Welcome to the deep dive. Let's kick things off with a visual. Imagine like a big movie poster and then the little ticket stub version of it.
Right.
Same image, just different sizes,
Exactly.
That basically, in a nutshell, is what we're exploring today. Geometric similarity.
Exactly. Same shape, different scale. It's like, think of a recipe. You can double the ingredients, get a bigger cake, tastes the same. Similarity in geometry is,
Right.
well, similar.
Right.
But just to be really clear, that's different from congruency. Congruent shapes are perfect replicas, same shape and same size,
Yeah.
like identical twins.
Okay.
So congruent figures are always similar, but similar figures aren't necessarily congruent. Size can differ.
Got it. So our deep dive today is all about these similar shapes, and specifically we're zeroing in on triangles.
Right.
Now, what's the kind of magic formula that makes two triangles similar?
Well, the sources point to two key things.
Yep.
Their corresponding angles have to be equal, and their corresponding sides have to be proportional, which means the ratios of their lengths are equal. It's like all the sides are scaled up or down by the exact same factor.
So if you picture one triangle, maybe the original, and the other's like a resized version,
Yeah,
zoomed in or out.
precisely. The angles inside, they stay the same.
Yeah.
And the ratio between, say, any two sides in the original triangle will be the same as the ratio between the corresponding sides in the resized one.
And there's a specific shorthand for this similarity, isn't there? It looks like, oh, ABC, EPQR.
Yeah.
We read that.
At the
Just triangle ABC is similar to triangle PQR.
That's it. But, and this is important, it's not just a random jumble of letters. That order, it's like a secret code.
A secret code. How so?
It absolutely is. That order tells you exactly which angles in triangle ABC match up with which angles in triangle PQR, and therefore which sides correspond. So in PQR, it means angle A matches angle P, angle B matches Q, and angle C matches R.
Right.
And because of that specific matching, side AD corresponds to PQ, side BC corresponds to QR, and AC corresponds to PR. That order is your key, really. It unlocks all the relationships.
Okay, let's really dig into this correspondence idea then. The material highlights that in similar triangles, the sides opposite those equal angles are the corresponding sides.
That's the connecting.
So let's take an example. Say we have ABC, O, PRQ. Notice the order change there.
Yeah.
PRQ. And we know angle A equals angle P, angle B equals angle R, and angle C equals angle Q. What does that tell us about which sides pair up?
Okay, so if A matches P, the side opposite A, which is BC, must correspond to the side opposite P, which is QR.
BC and QR.
Yeah. And angle B matches angle R, so the side opposite BAC corresponds to the side opposite R, which is PQ.
AC and PQ.
And finally, angle C matches angle Q, so side AB corresponds to side PR.
AB and PR? Got it.
And because they're similar, the ratios hold. BC over QR equals AC over PQ equals AB over PR. The same scaling factor applies to all corresponding pairs.
That makes sense. Now, what happens if we shuffle those letters again in the similarity statement? Say ABC, APRP this time.
Okay, QRP.
How does that little change in order affect our view of the corresponding sides and their proportions?
Well, that seemingly small switch.
Yeah.
It changes everything. If ABC card, now angle A matches angle Q.
A matches Q.
Angle B matches angle R.
B matches R.
And angle C matches angle P.
C matches P.
So the side opposite A, BC, now corresponds to the side opposite Q, which is PR.
PC and PR now.
AC opposite B now corresponds to PQ opposite R.
AC and PQ.
And AB opposite C corresponds to QR opposite P.
AB and QR.
So the proportions become BC divided by PR equals AC divided by PQ equals AB divided by QR. See, that order is like a precise instruction manual. You have to follow it.
Absolutely crucial. Like getting the address right, otherwise things go to the wrong place. Now, our sources also mention this works in reverse. If we know two triangles have corresponding sides that are proportional, what can we say about their angles?
That's another really powerful connection. If the sides are in the same ratio, let's say we have ADC and AEFD, and we know that ABF equals BCDF equals ACDE.
All three ratios are equal.
Right. Then the angles opposite those proportional sides must be equal. So angle C opposite AB must equal angle D opposite EF.
Okay.
Angle A must equal angle E, and angle B must equal angle F.
So it's a two-way street. Equal angles imply proportional sides, and proportional sides imply equal angles. That's fundamental.
It really is.
Now, the material also uses a visual to really kind of nail the difference between similar and congruent. Can you paint that picture for us?
Sure. Imagine two triangles again, ABC and OFFA, if they're congruent.
Congruent.
They are identical. Perfect copies. Side AB is exactly the same length as side FE. BC equals ED. AC equals FD. angles match perfectly too. You could place one exactly on top of the other.
Like a photocopy.
Exactly. But if they're just similar, say ABC, AFE, their angles are still the same. Angle A equals F, B equals E, C equals D. But their sides are just scaled versions. Maybe AFD is twice as big as ABC. So AB would be half the length of FE, BC, half of ED, AC, half of FD. Same shape, different size.
Right. Congruent is the photocopy. Similar is like resizing an image digitally. The content's the same, but dimensions can change. And there's one more interesting property you mentioned. Triangles similar to the same triangle.
Ah, yes. They are also similar to each other.
Okay.
Think about it like this. If, say, triangle X is similar to triangle Z and triangle Y is also similar to triangle Z, then triangle X must be similar to triangle Y. It's like that transitive property in algebra, but for similarity, a useful chain reaction.
Okay, solid foundation on what similar triangles are. Now, how do we actually prove similarity without, measuring every single angle and side?
Right, that would be tedious.
Our sources lay out some handy shortcuts. Postulates. Let's start with SAS similarity.
Has side-angle side similarity. This one says you have one angle in one triangle equal to an angle in another triangle.
Well, one pair of equal angles.
Yes, and the sides that include or form those equal angles are proportional.
Ah, the sides next to the angle.
Exactly, the arms of the angle.
Yeah.
If those conditions are met, equal angle, proportional including sides, then the triangles are similar.
So like in ABC and ODEF, if angle A equals angle D, and the ratio AB over DE is the same as AC over DF.
Then boom, ABC, the A of EF by SAS similarity.
And the key is those sides have to be the ones hugging the angle. Like if angle B equaled angle E, we'd need ABDE and BCEF to be proportional.
Absolutely. It has to be the included angle. The sides must frame that matching angle for SAS to work. It locks in the shape.
Got it. Okay, next up, AS similarity, sometimes called AAA.
Right. AA, angle,
Yeah.
or sometimes AAA, angle, similarity.
Yeah.
This one's a real workhorse, very useful.
Why is that?
It simply states that if two triangles have just two pairs of corresponding angles that are equal,
Only two pairs.
only two, then the triangles must be similar.
But why AAA then?
Well, because if two pairs of angles match, the third pair has to match too, right? Since all angles in any triangle add up to 180 degrees.
Ah, of course. The third one's determined automatically.
Exactly. So finding just two pairs of equal corresponding angles is enough. If you have ABC and DEEF and angle A equal D and angle B equals angle E, you can stop right there and say ABC. DEEF by AA similarity.
That sounds incredibly efficient. Two angles and you're done.
It really is.
Okay, and then there's SSS similarity. That one sounds like it's all about the sides.
You nailed it. SSS, side similarity. That says if all three pairs of corresponding sides of two triangles are proportional.
All three ratios match.
All three. So if you have ABC and PQR and you find that ABQR equals ACPR, then the triangles are similar. Even if you don't know a thing about their angles initially, the proportional sides guarantee the angles will match up correctly.
These postulates are like our cheat codes for proving similarity.
Hey, you could call them that. They save a lot of work.
Now, just circling back quickly to the notation, ABC, DEF. The sources really hammer home how important that order is. Can you just underscore why again?
It's absolutely critical. It's not just about neatness. The order ABC, WDF is a direct instruction. It tells you angle A corresponds specifically to angle DB to EC to F.
Okay.
It also tells you the side connecting A and B, that's AB, corresponds to the side connecting D and E, DE. AC corresponds to DF, BC to EF.
Right.
If you wrote, say, DBGC, ADFE, you'd be making a completely different statement. You'd be saying A matches D, but B matches F, and C matches E.
Which would likely be wrong.
Exactly. It leads to incorrect conclusions about side proportions, too. So that order ensures mathematical precision and avoids any confusion. It maps everything correctly.
Clarity is key. Avoid geometric mishaps. Okay, we've got the definitions, the rules, the notation. Let's see this stuff in action. Our sources have some great examples, starting with something called the right triangle altitude theorem. What's the big idea there?
This is a neat one. The right triangle altitude theorem describes what happens when you draw an altitude that's a perpendicular line from the vertex of the right angle in a right triangle straight down to its hypotenuse.
Okay, dropping a perpendicular from the 90-degree corner to the opposite side.
Right. And what's remarkable is that this altitude splits the original big right triangle into two smaller right triangles. And these two smaller triangles are similar to each other. And each one is also similar to the original big triangle you started with.
Wow, so you get like 3 similar triangles nested together.
Precisely. It's a beautiful cascade of similarity.
Our notes show a proof. Let's say we have triangle ABC, right angled at A, and AD is the altitude to the hypotenuse BC, hitting it at point D. How does that AA postulate we just talked about show that, say, ABA is similar to ABC and both are similar to the original ABC?
Okay, let's break it down. Compare the small triangle DBA with the big one, ABC.
DBA and ABC.
They both share angle B, right?
Yeah, angle B's in both.
And DBA has a right angle at D, while ABC has its right angle at D.
So 2 angles match, angle B and a right angle.
Exactly. That's AA similarity. So DBA, CBA. Note the order. B matches B, the right angle. D matches the right angle A. So A must match C.
Okay, DBA, CBA. Now what about the other small one, BD, and the big one?
Same logic. Compare DD and ABAC, which is the same as ABC. They both share angle C.
Angle C is common.
And AD has a right angle at D, while BC has its right angle at A.
Another A match.
Yep, so DDC, C matches C, right angle D matches right angle A, so A must match B.
So DDA. And since both small triangles, DBA and DAC, are similar to the big one, ABC.
And it must be similar to each other. That transitive property again, so DBA, TDC.
That's really elegant how they all connect. And I bet that similarity means there are some interesting relationships between the side lengths.
Absolutely, that's where the power comes in. Because of these similarities, you get some really useful proportions. For instance, one key result is that the length of the altitude squared, AD shore, equals the product of the lengths of the two segments it creates on the hypotenuse. So AD shore equals BD times DC.
AD squared equals BD times DC.
Wow, it comes directly from the similarity, specifically a DBA, BDC. It essentially means the altitude is the geometric mean of the two hypotenuse segments. Very handy for finding unknown lengths.
Cool. Okay, let's switch gears. Example 2 involves parallel lines and transversals. How do parallel lines create similar triangles?
Well, when you have parallel lines cut by another line, a transversal, you automatically get pairs of equal angles. Think alternate interior angles, corresponding angles.
Right, those geometry basics.
Exactly. Now, imagine a situation where you have a point, let's call it O, and several lines radiating out from O that cut across two parallel lines, say line L and line M.
Okay, lines spreading from a point hitting two parallels.
The triangles formed between point O and the points where the lines hit the parallels. They end up being similar. The parallel lines essentially force the angles to match up.
How so?
Let's look at the figure in our notes. Lines through O hit parallel line L at ABC and parallel line M at PQR. Consider triangle OAB and triangle ORQ.
OAB and ORQ.
Since L is parallel to M, line OR is a transversal. Angle OAB and angle ORQ are alternate interior angles.
So they're equal.
Yes. Also, angle AOB and angle RQ are vertically opposite angles at O.
Also equal.
So we have two pairs of equal angles. By AA similarity, OAB, OQ, OAQ.
Okay, that makes sense.
You can apply the exact same logic to show that, say, OBC is similar to OAQP. Vertically opposite angles at O again, and alternate interior angles using transversal OQ.
So OBC, OQP.
Right. And because we have these similar triangles, their corresponding sides are proportional. From OAB, we get OAB, OBQ, OB2, OQ from OB2. For the OBQ, we get OBQ, OQ, OCA, PCQP.
Ah, look, OPQ appears in both sets of ratios.
Precisely. So we can link them. We have ABRQ, OBQQ, and BCQP equals OBUQQ. Therefore, ABRQ must equal BCQP. Or rearranging slightly, ABC equals RQQP, or QOPQ.
So the segments cut on one transversal, ABC, are proportional to the segments cut on the other, RQQP. That's a direct result of the similar triangles formed.
Exactly. Parallel lines lead to proportional segments via similarity.
Clever. Okay, example 3 gives us some angle relationships and asks us to prove similarity. We're given angle QPS equals angle RC and angle PRQ equals angle PTS. We need AA similarity, so we need two pairs of equal angles within the triangles PQR and PST.
We already have one pair. APRQ and APQR equals APTS and DPS.
Good. Now we need another pair. Notice the angle APR. It's part of the bigger angle AQPR and also part of AQPD.
It's shared. Well, almost. It's between the bits we know are equal.
Exactly. Let's use the first given fact, AQPS, AQPT. If we add that common angle, AQR, to both sides of this equation.
Add DPR to both. We get AQPS plus APR, APT plus APR.
Okay.
Now look at the diagram. AQPS plus APR makes up the whole angle APPR.
Right.
And APT plus APR makes up the whole angle APT.
Ah, so AQPR equals ASBT.
There's our second pair of equal angles. So we have APRQ, APTS given, and APR, AT, which we showed. That's enough for AA similarity.
So PQR, PST, nice deduction.
Mm-hmm.
And then because they're similar, their sides are proportional. The problem gives PTST as 3.4 and asks for QRPR.
Okay, since PQR, PST, we need to match the corresponding sides carefully using the angle equalities.
Right.
We know APR, QR, APTS, so the sides opposite these angles correspond. PQ corresponds to PS.
PQ to PS.
We know AQPR equals APT, so the sides opposite these correspond. QR corresponds to AT.
QR to PT.
So the ratios are equal.
Yep.
QRST, PRPT, PQPS. We want the ratio QR to PR. Let's use QRST, PRPT.
Even rearrange that to get QRST, RSTPT.
Just cross multiply or swap PR and ST.
Right.
We are given PTST equals 34. So SEPT is just the reciprocal of that.
43.
Exactly. So QRPR is 43. The ratio QRTR is 4:3.
Excellent. Using similarity to find a ratio. Now, example 4 uses similarity to find an actual unknown length. We have two vertical lines, AB and DE, both perpendicular to a horizontal line BC.
Like two posts standing on the ground.
Yeah. We know AB 9 centimeters, DE 3 centimeters, AC 24 centimeters. AC is the line from the top of the taller post to the base of the shorter one's perpendicular point on the ground line. We know C is a point on the ground line.
Let's clarify. AB is perpendicular to BC at B. DE is perpendicular to BC at E. C is a point such that ADC are collinear. So AC is the hypotenuse of the big right triangle ABC, and DC is the hypotenuse of the small right triangle DEC.
Okay, got it. ADC are on a straight line, and we need to find the length of AD.
First step, prove the triangles are similar. Look at ABC and DEC.
ABC and DEC.
They both have a right angle. ABC is 90 degrees in ADC.
Right angles check.
And they both share angle C. Angle ACB is the same angle as angle DCE because ADC are collinear.
Shared angle C, check. Two pairs of equal angles.
So,
Asimilarity. ABC, DC.
perfect. Now that we know they're similar, we can set up the proportions using corresponding sides.
Okay. In ABC, the side opposite angle C is AB. In DEC, the side opposite angle C is DE. So AB corresponds to DE.
Good.
And the hypotenuse in ABC is AC. The hypotenuse in DEC is DC. So AC corresponds to DC.
Excellent. So the proportion is...
ACDC equals ABDE.
Precisely.
Yeah.
Now plug in the numbers we know.
AC is 24. DC is what we need. Well, part of what we need. AB is 9. DE is 3. So 24. DC is 9. 3.
Okay, solve for DC. 93 simplifies to 3.
Right. So 24 DC equals 3, which means DC equals 24, 3.
Which is?
8 centimeters. DC is 8 centimeters. But the question asks for AD.
Look at the line ADC.
Yeah.
We know the total length AC, and we just found the length DC.
Right. AD is just the difference. AD equals ACDC.
There you go.
So AD equals 24 centimeter, 8 centimeters. It's 16 centimeter.
See, similarity helped us find that missing piece.
Very practical. Okay, final example. Back to the altitude on the hypotenuse of a right triangle. Triangle ABC, right angled at AAD, is the altitude to BC. This time, we need to prove ABD is similar to BAD, the two smaller triangles.
Right, we already established earlier they were both similar to the big one, so they must be similar to each other. But let's prove it directly using angles, maybe by chasing them around.
Okay, how?
Let's assign a variable to one of the acute angles. Say, let angle C is X.
Okay, angle C is X.
In the big triangle ABC, angle A is 90 degrees, angle C is X, so angle B must be.
180, X is 90, X, angle B is 90 minus X.
Perfect. Now look at the small right triangle ADC. Angle at D is 90 degrees, angle C is X, so the third angle, angle CAD, must be.
180X equals 90X. So angle CAD is 90 minus X.
Good. Now look at the other small right triangle, ADB. Angle D is 90 degrees, angle B is 90x. So the third angle, angle BAD, must be
180x with 190 plus x, angle BD is x.
Exactly. Now compare the angles in ABD and DCAD.
In ABD, we have angle B equals 90x, angle BAD, and angle ADB equals 90.
And in ACAD.
We have angle C, x, angle CAD, and angle 90x, and angle CDA equals 90.
Do we have two pairs of equal angles?
Yes. Angle BDX equals angle CX, and angle B90x equals angle CAD and 90x.
So by AA, similarity.
ABD.
Nay.
Proven directly.
And as we saw before, this similarity leads to that useful proportion involving the altitude. Which sides correspond? Let's see. Side opposite angle B, 90x and DBD is AD. Side opposite angle CAD, 90x and CAD is CD. So AD corresponds to CD.
AD corresponds to CD.
Side opposite angle BX and DBD is BD. Side opposite angle CX and DOCAS is AD. So BD corresponds to AD.
BD corresponds to AD.
So the proportion is ADCD, BD, AD.
ADCD, EDCD if we cross multiples.
We get AD, AD, BD, CD, or AD, AD, or I give us BDX, CD. that key relationship again.
And the example gives BD equals 3.6 centimeters and CD equals 6.4 centimeters. So we can find AD.
Yep, AD equals 3.6, 6.4.
Oh, let's see. 3.6 times 6 is 21.6. 3.6 times 0.4 is 1.4. And add them. 23.04.
Right, AD equals 23.04. So AD is the square root of 23.04.
Square root of 23.04. Well, square root of 25 is 5. Square root of 16 is 4. It ends in 0.04, so maybe something ending in 0.2 or 0.8. How about 4.8? 4.8, 4.8. 4.48 is 50 to 2. 52 could total 200. 200 plus 4 plus 2 plus 4. No, wait. 40, 40, 6, 7, 2408, 640, 88, 64. 1600 plus 6640 plus 64 plus 64 is 2304.
Yeah, good mental math. So AD equals 4.8 centimeters.
Fantastic. And it's worth just stating those three similar pairs again from this altitude situation.
Sure. We have the two small ones similar to each other, ABD, KCAD. And each small one is similar to the original, ADD, ABZ, using the angle matching we did, and JCAD, CBA. These lead to those other useful squared relationships too. ABV equals BDXBC and AC shade deer, CDXBC. Lots of power packed into that one diagram.
This has been a really thorough deep dive into similar triangles. We started with that basic idea. Same shape, different sides.
Proportional sides, equal corresponding angles, yeah.
We were careful to distinguish it from congruency, that identical twin idea, and stress why that vertex order in the notation, like ABC, PQR, is so absolutely critical.
Can't emphasize that enough. It's the map.
Then we got our shortcuts, the postulates, SS.
Side angle side, equal included angle, proportional framing sides. Angle, angle, just two pairs of equal angles needed. The real workhorse.
And SS.
Side, side, side. All three pairs of sides, proportional.
And those examples really showed the power, didn't they? From the elegance of the right triangle altitude theorem.
Creating that cascade of similarities.
Yeah, how parallel lines neatly generate proportional segments.
Via those forced equal angles.
And just the practical application of using these similarity ratios to find lengths or other ratios we didn't know.
Absolutely. It turns abstract geometry into a problem-solving tool.
It's amazing how these fundamental geometric ideas just pop up in so many different places. So for you, the listener, as you go about your day, maybe take a second to look for similarity. Think beyond the obvious maps or scale models.
Yeah, look at architecture, how blueprints relate to buildings, how motifs might be scaled, or photography capturing a huge landscape in a small photo.
Or even manufacturing, making parts in different sizes but the same fundamental shape.
Exactly. Consider how those principles we discussed, the equal angles, the proportional sides, are playing out in those situations. What does that constant scaling relationship tell you about structure, about design, about how we represent the world?
That's your challenge for today. Something to mull over. Until our next deep dive.